All right, section 5 of chapter 8 is on dilations, which is the last type of transformation that we're going to be talking about. Um, so it is the only transformation that is not an isometry. Remember, isometry means that the preimage and image are congruent. On this one, a dilation makes a figure either bigger or smaller. If the So they're going to give you some kind of scale factor. If the scale factor is bigger than 0, the image is going to be bigger. I'm sorry, if the scale factor is bigger than 1, the image is going to be bigger than the original. If the scale factor is in between 0 and 1, it's going to be smaller. If it's exactly 1, it's going to be the same size. It's not really a dilation. It's just a copy of itself. So they call it an enlargement if the scale factor is bigger than 1, and a reduction if the scale factor is between 0 and 1. So we're just going to do some examples of the types of problems that you'll be asked to practice. Here are some examples of an enlargement and a reduction. So in this one, they tell you the scale factor is 2. So since the preimage D to C, the segment DC is 2, you multiply it by 2 and you get the new length of 4. On this one, the scale factor is 1/4. It's a reduction. So since the original, the preimage length was 8, 1/4 of that gives you a length of 2. So this is a pretty easy one. They're going to say, is the dilation an enlargement or a reduction? And then what's the scale factor of that dilation? The original one is not going to have the prime notation on the vertices. So it looks like this is the original, and then this big triangle is the new image. So if the preimage is smaller than the image, this obviously is an enlargement, because the new one is way bigger than the original. Now, the scale factor is not 2. You don't just look at the numbers. Just because this is 4 and that is 8 doesn't mean that it's twice the length. Remember, this 8 is really just talking about from there to there, from the original T to T prime. So if you were to include all the way down to X, the whole length is actually 12. So from here to there is a whole length of 12. So if the original length of the corresponding side is 4 to the new length of 12, that's a scale factor of 3. So I just say SF for scale factor is 3. So that's how you do it on a picture like that. Sometimes you'll be given a graph, which can pose a little bit of a harder problem. So you might have to do the distance formula if all of the sides are diagonal or some kind of slant, unless you notice KL and K prime L prime. Notice those ones are straight up and down. So those ones you can just count. So notice, by the way, I guess we should say, is this an enlargement or a reduction? This is the original because there are no apostrophes. This is the new one since there are. The original one is bigger. It got smaller, so it's a reduction. Now, since these are vertical, we're able to count them. I'm going to give you the distance formula just in case. I don't remember if any of the problems need it. But if all of the segments are slanted, remember the distance formula is the difference of the x's squared plus the difference of the y squared, and then the square root of all of that. So, luckily for us, though, on this problem, we can just count. KL goes from 0 down to -4. That's a length of 4. K prime L prime goes from 0 to -2. That's a length of 2. This one got from 4 to 2. That's half the size. So the scale factor is 1/2. Always put the scale factor, I think, as a fraction, by the way. All right, to the back. Here's some other things you're going to be doing. You're going to be given some coordinates. You're going to plot those coordinates, and then you're going to find the coordinates of its image after a scale factor that's given to you, and then you're going to graph that as well. All right, so P is at 2, 0. G is at 0, -2. And Z is at -3, 1. So P, G, Z. And then again, I like to use that straight edge because I like my picture to look good. So let me just draw those lines real quick. Okay. So those are the originals. All right, so this is very simple too. If my scale factor is 2, it wants me to write what the new coordinates will be and then graph those. So if my scale factor is 2, all I have to do is multiply that to each of the coordinates. So if P is at 2, 0, P prime, multiply both of those by 2, is 4, 0. If G is at 0, -2, multiply those by 2, and G prime is at 0, -4. And if Z is at -3, 1, multiply those by 2, and Z prime is at -6, 2. And then we just have to plot those, and then we'll be done. Might look at some things. So P prime is here, G prime is there, and Z prime is left 3 and up 1 more, Z prime. And then we'll connect these. So you can look at the original and the new one, and you'll notice that corresponding sides are going to be parallel. Corresponding sides are also going to be twice the length of the original because of the scale factor of 2. And I believe the area is also it takes up twice the area as the original. So they all kind of correspond. And remember, the shapes are similar because the angles are going to be congruent also. Okay, this time we're going to take that same PGZ, that triangle, and this time we're going to do a scale factor of half. So let's go ahead and plot the original. Z's there, P here, and G. So we know that it's going to get scale factor is 1/2. It's going to get smaller. Okay, so we take each of those coordinates of the original over here, and we're going to multiply them by 1/2. So P, I'm going to call it double prime this time just because it's kind of really the second one, is going to be at 1, 0. G double prime, if it was at 0, -2, times 1/2 is 0, -1. And then Z double prime, let's see, half of -3. You can either think of it as -3/2. That's not really helpful for graphing, but -3/2 is -1.5. Half of 3 is -1.5. And half of 1, again, you can think of it as a half, but I like to think of it as decimals when graphing. It's 0.5. So P would be right here, G is right there, and Z is left 1.5 and up 1/2. It's like right about there. So again, this new figure is exactly half the size of the original. And don't forget to label those vertices. So there you go. It's not too difficult. Just multiply each part of the coordinate by the scale factor. Last type of problem says a magnifying glass shows you an object or an image of an object that is 7 times the object's actual size. So the scale factor of the enlargement is 7. It's 7 times, so scale factor is 7. Makes sense. Here we go. This is a apple seed under that magnifying glass. What is the actual length of the apple seed if, in the magnifying glass, the apple seed is 1.75 inches? So if this has been enlarged and now it's 1.75 and it's 7 times the original, how would we get back to the original? Well, of course, divide. So all we have to do here is take 1.75 and divide it by 7. And I believe that's nice and easy because you think about money. If you had 7 quarters, that would be $1.75. So 1.75 divided by 7 is 0.25 inches. So the original apple seed is 0.25 inches. This section, again, not that difficult. If you have any questions, just email me or ask a friend. You should be just fine. Good luck. Get started on your assignment.